Hello there, and welcome to my spring of 2021 seminar presentation. I wasn't able to record the live session that occurred, but this is the recording then of the presentation, and I'm just giving it again for everyone else on YouTube who wants to check out this video after the fact. Uh, and so the title of this presentation is Investigating GLM Flash Optical Energy Measurements with ABI and MRMS Datasets. Uh, I'm Kevin Thiel. I'll be presenting this today, uh, along with my advisors, Dr. Kristen Calhoun, Anthony Reinhardt, and Don McGorman from the NOAA National Severe Storms Laboratory, and also the University of Oklahoma's Cooperative Institute for Mesoscale and Meteorological Studies. And I thank them very much for their help along the way as we've been studying the forecast applications of the Geostationary Lightning Mapper over the previous 2.5 to 3 years now. So a quick review of the Geostationary Lightning Mapper for those who maybe don't know. The GLM is a space-based optical lightning sensor that is on board both the GOES 16 and GOES 17 satellites, which covers a vast majority of the mid-latitude and tropical Western Hemisphere. I can see the instrument pictured there on the far right. It is essentially a large, high-speed camera. What the GLM does, though, is it doesn't detect certain parts of lightning that you would expect from certain ground-based sources. It is is finding individual events within the GLM array. Those individual events, or the pixels from the GLM, you can see down here at the bottom in this diagram, are then put together in the adjacent 2 millisecond frames that the GLM records and put into groups. Those groups are then clustered spatially and temporally into a singular flash. So that's kind of the hierarchy of that data. This figure here on the bottom left, in this 4-panel plot, we can see what the GLM data would look like. This is a case from Running et al. 2019. And as we can see, it's difficult to really get at what's happening electrically within convection when we view the data just straight as these event sources or these events, groups, and flashes all at the same time. You can get at some features, but it's hard to really characterize quickly what is actually happening within the storm. And so what was developed was an open source Pythonic package called GLM tools. And this takes the footprint of the data created by the events of each flash and then is able to create these spatially continuous gridded products. And these can be used operationally and are being used currently within National Weather Service forecast operations and are also of scientific use as well and for further studies. So you might have seen other lightning location systems before, or LLSs, but how does the GLM compare against those? So this is 1 minute of a case study that we had run back from June 12th, 2019. And when looking at this case study, you can see on the far left side, we can see what the NLDN data would look like with a few flashes, Earth networks, also including the intracloud flashes as well. We can see a higher fraction of those flashes all on the western side of this plot. This is 1 minute of data now from the Oklahoma Lightning Mapping Array, which plots the individual sources that are emitted as the flash propagates. So it's very high resolution spatially and temporally within a limited region. And we can see all of the sources and all the flashes that occurred within that area, along with these larger flashes off to the east. What the GLM is able to do through GLM tools is create products such as the flash extent density, which is the number of flashes that propagate through an area over a given period. So in this case, 1 minute. So we can see the higher FED values on the western side, which correspond with the higher source points from the LMA. We also have flash area as well. This is the average flash area, but we'll also be showing a lot more of the minimum flash area later. And that one's going to be a little bit more useful. But this gives us the average of all flash areas that propagate through the given pixel over that 1 minute. So we can see the larger flashes off to the east, and we can see the large flash off to the east here too. With total optical energy, this is one of the most native formats for GLM data. It is simply the accumulation of the light that is emitted from the flashes over that given time period. So we're just seeing where the accumulated light is the brightest over that period and what the GLM is actually observing in that area. So we've already discussed several things so far throughout my work as a master's student, and also a publication that came from that, Thiel et al. 2020. And the reference for that will be at the end of the presentation. But within this bulk GLM and ABI study, we showed that as you increase your thunderstorm severity in terms of, or from the perspective of the ABI, looking at cloud top temperature and cloud top height, we showed that the flash extent density increased while minimum flash area decreased, and that's physically consistent. So in these plots on the bottom, what we've done is we've taken this very large data set, over 4 million points, comparing our cloud top height and temperature from the ABI with our GLM variables, and we sampled the median value within each bin as a function of temperature and height. And we can see that as we go to these higher and colder cloud tops, that we observe higher flash rates. We also see that those flashes are smaller, which is physically consistent, as when you are near a strengthening updraft, you would expect to see these smaller regions of charge that then initiate flashes more rapidly. This is especially true when looking at this compared to local storm reports. And so this is our kind of severe thunderstorms in this case. And we can compare between this figure and the current figure, that we see an increase in FED and a decrease in MFA, and that those relationships are actually amplified in this kind of case. To really drive home the point, we then also showed a few case studies, one of them being a supercell across southeastern Kansas, and we observe exactly what you would expect, high FED values associated with the storm, especially around the time when we had local storm reports, tornado, hail, and wind reports within this zone. Our minimum flash areas also decreased down to their smallest available values, right around 100 square kilometers. And so what this is able to show is that this is a pretty consistent signal, and this is something that's good to be seeing overall in an individual storm data, and is something that is usable for both the severe storms research communities and then also for forecasters that are dealing with complex and dynamic convective environments. Now the real question, and we kind of kept total optical energy away from this study just because we knew it might complicate things. And if we included it in the case study, of course it did. So this is what the total optical energy now looks like for that same storm. And what we can see is the increase in our total optical energies around 2030 UTC, carrying until about 2100, just after maybe to 2110, with our maximum total optical energy pixels right around 800 to 1000 femtojoules. But right before the period of maximum severity of this case, the total optical energy drops from this higher values down to about 200 to 300 femtojoules instead, and stays there for about 30 minutes until near the end of this case. And so the real question is, well, what happened? Why does this signal appear? And this is actually a signal that has been observed in other cases. And so when we are able to apply it to this case, now this gives us leverage to understand, well, how can we fit total optical energy into this picture? And how can both forecasters and researchers use this moving forward? So one idea that we had to help address this when thinking about the changing optical properties of the thunderstorm, it's great to be looking at cloud top like we did with the advanced baseline imager, but now we need to look inside the storm itself. And so we're going to be looking at some isothermal and vertically integrated MRMS variables to help us understand the varying optical path of lightning flashes relative to the GLM. We'll be looking at three variables in particular, the first one being the negative 10 degrees Celsius isothermal reflectivity. Now, at the negative 10 degrees Celsius isotherm, that is the start of the mixed phase region, where you would expect to see charge separation through the non-inductive mechanism, and this is an indicator when you have higher reflectivity values in that zone of increasing lightning production, thunderstorm severity. And it also, when plotting, is a variable that we're used to looking at as well. And so it helps us to also interrogate thunderstorm morphology as we progress through certain case studies later on. The next variable we'll be looking at is the maximum expected size of hail, or MESH. And MESH is actually also a product of the severe hail index, which in that case is a vertical integration of the reflectivity between the freezing level and the radar indicated cloud top height. And so when looking at cases of severe hail, that will of course tell us not just thunderstorm severity, but also give us a sense of where those hail cores are with respect to our lightning production. Vertically integrated ice is another variable that we'll be using as well, which is vertically integrated between -10 and -40, and between those isothermal levels. And so we can use those as well to assess the amount of ice and the amount of kind of stuff that a flash has to propagate through in order to reach cloud top and be observed by the GLM. And so we'll be using these three variables throughout the study and later on to help us kind of figure this all out. So to put this all together, this is what we're setting out to do. We are adding the variables that are in bold on the left-hand side here in the red box, and this is the total optical energy, along with our same GLM and ABI variables. We then are adding the MRMS variables that we mentioned in the last slide, along with, from before, our local storm reports for severe hail, wind, and tornado occurrences. Putting this all together into our big data set, we'll be following the same methodology from Thiel et al. 2020 with a max bin sampling for both the GLM and ABI variables. This backs out our resolution to 20 kilometers, but this was shown to be fairly effective from that study. With the MRMS data, because the initial 20-kilometer data is actually projected onto a the geostationary coordinate system from satellite view, we had to take the MRMS data and put it on that same satellite perspective. But the MRMS data doesn't come like that. So we had to use a specialized method with a KD tree and sampling the maximum value within a radius of 15 kilometers. The 15 kilometers is somewhat important because this helps us to offset differences between where we would undersample or oversample, depending on what area we were observing within the CONUS. We also only looked at the CONUS east of 103 degrees west. That way, due to data quality within the MRMS products themselves, especially the vertically integrated products too. And then lastly, with our local storm report integration, we flagged all points within about 30 kilometers and plus or minus 5 minutes of all points. And if you're wondering, we do not double dip in any case there. So if there are 3 wind reports all at the same time in the same area, that point will only be marked once. So our compiled data sets now look like this. We have our original 4.6 million GLM and EBI samples from before. We now have over 2.8 million GLM and MRMS samples across the Eastern CONUS within the MRMS domain, and also our over 9,500 storm reports that we can also now pull from within this study. So when looking at those previous contour plots from before, we now added in the total optical energy variable and sampled their median values. And so what we can observe is as we increase in our total optical energy values, that those do actually increase in the same area that we saw with correspond to the FED. FED is often corresponded quite well with total optical energy, kind of the simple idea of more lightning, more light. And so this generally increases and is slightly larger for severe cases, but that signal wasn't as strong as what I personally would have liked. And so my question was, well, there's an increase there, and that's good, but is it enough? Is it significant? And so what I'm going to show on the next slide is some significance testing that was handled, where we actually are looking at comparing the points that were sampled here in the severe cases versus some randomly sampled points in non-severe cases. And so when comparing these, we did a Monte Carlo simulation with over 10,000 iterations, sampling randomly, using the same bin size from the that did contain the local storm reports against those that did not. Sampling the median value each time, we did that 10,000 times, and then composited that data and the data that was all flagged versus LSRs versus those that were not. Our red shading is defining in the plots below the areas of significance using a one-tailed 95% confidence. And what we observe is that across a variety of cloud top heights and temperatures that we do observe with the flash extent density and minimum flash areas, essentially significance, which is really nice to see. However, with total optical energy, that image is a little less clear. We do see some areas of significance at the very bottom and at the top of our spectrum of kind of available cloud top temperatures and heights, and that may have some significance as the strongest of the strong storms, and potentially even in this case be looking at some of the trailing stratiform regions of mesoscale convective systems, but it really doesn't paint that clear of a picture that we're able to actually pull from as compared to the FED and MFA values. So our first big takeaway is that the GLM, FED, and MFA do show significant increases/decreases when comparing severe versus non-severe convection. However, the GLM total optical energy does not show significant increases. And now we've kind of established that. Why is that so? And so we'll use the MRMS data and look at the optical properties of the severe convection and try to get at, well, what are we actually observing within the convective cloud itself? And what can we then discern about the optical characteristics of those flashes in a representative manner? So we'll first start by looking at the GLM data versus the negative 10 degrees Celsius isothermal reflectivity. And so what we've done within these violin plots is we've taken all of our GLM data and we binned it by every 10 dBz in reflectivity and presented those within the violin plots, as we can see there, looking at the changes in the total optical energy as a function of reflectivity. What we observe with the total optical energy is we do see increases in the distributions up until about 20 to 30 dBz, but then it essentially flatlines and remains consistent throughout the rest of that period up into the higher reflectivity values. And so we see this drop off. Is that a kind of signal that we should really be looking at? And so in order to do that, we have to also put that in context with our GLM flash extent density and also our minimum flash areas. And when looking at those figures, a different kind of picture begins to show up. Sure, we do see increasing flash extent density values that should lead to increased total optical energy. However, with the minimum flash areas, we do see a peak in our minimum flash areas at around 20 to 30 dBz, which is commonly around where you'd expect to see within convective stratiform flashes, and in those areas, sufficient for charge separation, and then decreasing from there. So we do have an increase in our optical energy, but we have decreasing flash sizes. So these flash sizes that are smaller will then contribute less overall, unless they're in substantially small and targeted regions. There is also, depending on how we sampled the data, could also in some ways vary our results in some ways as well. And so we're really left with the question of, is this the effect of the optical depth and that changing within the storm, or the characteristics of the flashes themselves? And that's something that we aren't able to definitively say based upon this bulk study. So our second key takeaway that we'll just say for now, we don't have anything definitive from the bulk study, but that the total optical energy should be evaluated with respect to the flash extent density and the minimum flash area. So we've now assessed that within the bulk study, but how does the GLM data look in cases of discrete convection, and how does that correspond to our MRMS data? So we're going to go back to the case study that we started out with at the very beginning. thinking about that supercell that had high flash extent density values and then very small minimum flash areas. And what we can observe is that around 2100 UTC, we eventually see the presence of this hail core and of mesh values that are appearing significant and that are appealing that would be severe in those cases. And then around 2145 is when we start to see the considerable drop off in this supercell as it moves off to the northeast. I will let it play through one more time just so that way you can see it. But watch for that rise at around 2100 UTC of this supercell in the bottom left-hand corner, and you will see the forward flank of that supercell increase as well, and you can see really as that takes off. But note that a lot of our lightning production is going to be off and to the west around the convective updraft and in close proximity to that updraft. And so that's really going to be an important area to watch. Also note that the viewing kind of area and perspective of the GLM of this storm is essentially from the southeast, approximately, potentially more of the east-southeast. But this is kind of the idea of where the GLM is looking versus what's happening within that storm and where the light has to pass through in those cases. So when going back to our time series plot, the faded black line is now the total optical energy, reappearing there again, with the units in the table there on the right-hand side. On the left-hand side, though, this is looking at the MRMS mesh along with vertically integrated ice. They do have different units, but they're on the same table just to help consolidate the plot. And what we observe is that around 2110, when the total optical energy does decrease, is that we do see this increase in vertically integrated ice from about 50 kilograms per meter squared up to exceeding around 80 kilograms per meter squared. Then we see the mesh values there continually increasing and exceeding in those cases nearly 2 inches in those cases at their peak. Now, in order to keep this plot simple, it didn't show the maximum -10 degrees Celsius reflectivity, but that did exceed around 60 dBz and then drop below about 55 dBz around 2145 here at the end. And we can see as we have that drop off at the end, near the end of our severe period within that supercell, is that we did see a subsequent increase in our total optical energy. And so the question is, well, what really should that value of optical energy be in this area? Should there have been a higher range and then a drop off? Is there more light that should have been captured depending on the varying optical depth and the perspective of the GLM of this convection? So the last key takeaway that we're going to say is that the varying optical path of the convective cloud does appear to coincide with altered GLM total optical energy data. But the full extent of this impact is really to be determined because we really couldn't figure that out in the bulk study itself. Now, in this case, we did see that this was in cases of large hail. This has been observed as well before. And so maybe this could be the quote unquote hail spike of GLM data. If you have a case where you have high flash extent density values, everything on MRMS shows a severe storm, but then all of a sudden, the total optical energy just drops out. And based upon your location to the satellite, you can then observe, okay, we're seeing less energy because the cloud is becoming more optically thick due to large hail. And that can then further increase confidence in a forecaster in that kind of convective environment. It also can allow potentially in cases of poor radar coverage, that actually could also be useful as well, where FED remains high, but total optical energy suddenly drops during the period of maximum severity. So for some future work, we want to be kind of looking at that through additional case studies as a forecasting tool. We also want to, we're looking to integrate LMA data into our analyses when looking at flash initiation heights. As has been shown in a novel study by Brunner and Bitzer 2020, that can also be a nice, that flash initiation heights can have a substantial impact on the amount of light that is received from the geostationary lightning mapper. And then also comparing in terms of thunderstorm geometry, GO 17 as well being added in and its GLM. And so looking at this from kind of a dual GLM perspective, how can we leverage these optical characteristics to help us maximize the utility of the geostationary lightning mapper? I'll lastly put up my references, and so you can see everything that was cited throughout this presentation. Note the feel at all citation is down there as well, and that's something that I would encourage you to read. That has a little bit more insight there as well. And then lastly here, I'll leave up the key takeaway slide at the end. The email is in the bottom right. And thank you so much for coming to talk about the Geostationary Lightning Mapper today. And I hope that you can kind of take away from this, and hopefully we can continue to advance the operational utility of the sensor forward, not just from the operational side, but also including within severe storms research.